Hello, my name is Dominic Coccitti-Smith, and this is a presentation on carbon dioxide and how it acts as a forcing agent within climate change. So we'll discuss electromagnetic radiation and energy, history of carbon dioxide, the human contributions to carbon dioxide in the atmosphere, take a look at some changes in the concentration of carbon dioxide in the atmosphere from the Industrial Revolution to the present day. And then we'll talk about how to balance the amount of carbon dioxide in the atmosphere by reviewing the sources and sinks of carbon dioxide. So a forcing agent, those can be internal or external forcing agents. External to the Earth or internal to the Earth, kind of the physical processes that occur here on Earth. So let's start off with the electromagnetic spectrum. So as you can see, it spans from gamma rays to radio waves with changing wavelengths and frequency. So what hits the Earth from solar radiation, we'll see in a couple slides, is mostly UV, visible, and infrared, but it does span the entire electromagnetic radiation. And different forms of electromagnetic radiation have different energies. We'll talk about how energy and frequency are related on the next slide. So any object above 0 degree Kelvin is going to emit radiation. This could be in the form of infrared radiation or radio waves, gamma rays. So everything's going to emit some form of radiation if it's above 0 degree Kelvin because the molecules themselves, the atoms in the molecules, are moving, and that vibrational motion will emit some radiation. So electromagnetic radiation has a dual nature to it. It exists both as a particle and a wave. And this dual nature of electromagnetic radiation can be equated using a wavelength equation and a particle equation. So the wavelength equation here, C, that's the constant, the speed of light, or electromagnetic radiation, that stays the same. It's about 3 times 10 to the 8th meters per second, so pretty fast. And then lambda here, that's our wavelength, usually measured in meters or nanometers. And then nu, that's our frequency. That's how many waves pass by per second. And there's an inverse relationship here between wavelength and frequency. And another relationship is this particle equation. So the energy is going to be related to the frequency of that electromagnetic radiation. We multiply it by this h here, that's Planck's constant. It's 6.626 times 10 to the negative 34th joules times second. So each photon has a particular amount of energy that it can have, known as a quanta. And while that value is small, we're talking about a huge number of photons here. So remember that these photons, they have energy. And that energy in the form of radiation in those photons is usually going to be absorbed, and it will change the movement of another particle or the rotational or vibrational movement of the atoms within a molecule. And recall that energy is conserved from the law of conservation of energy. Now, related to energy is is movement measured with kinetic energy, and that's also related to temperature, as we'll see. So the equation for kinetic energy here is K equals 1/2 mass times velocity squared. So if the mass of an object remains the same, but the velocity would increase, perhaps it got bombarded by a bunch of photons, and its velocity increases, then we would see an increase in kinetic energy, which will also relate to an increase in temperature. So solar radiation, here we have a chart depicting the spectrum of solar radiation. We see that largely in the visible and infrared region. And we want to note here this black body radiation too that's emitted from the Earth as it reflects the solar radiation. So according to our author Bloom, there's 3 fates of radiation. It can be transmitted, reflected, or absorbed. Now, if it's absorbed, as in the case with certain types of electromagnetic radiation for carbon dioxide, that's also going to increase kinetic energy, which is going to increase the temperature. So carbon dioxide, it gets a lot of its energy from this blackbody radiation absorption here from the Earth. So carbon dioxide itself, it transmits some of the strongest energy in the form of electromagnetic radiation from the sun. That goes through the atmosphere, through carbon dioxide, and hits the Earth, then reflected back from the Earth. It gets absorbed. So this is that greenhouse effect that people talk about. The electromagnetic radiation comes in from the sun, reflects from the Earth, and then it gets absorbed by that carbon dioxide. So if there's more carbon dioxide in the atmosphere, there's going to be more absorption of that particular electromagnetic radiation, usually found around here in terms of wavelength. And then that will also increase our temperature. So looking at the history of global carbon dioxide, about 4.1 billion years ago, the atmosphere was largely formed by the result of gases from volcanoes. And these had high concentrations of carbon dioxide and other greenhouse gases, like our nitrous oxides, water vapor, and methane. And with that high concentration of carbon dioxide, some of the first successful forms of life evolved, and those were known as cyanobacteria. Cyano for the color blue, and bacteria as the prokaryotes. They don't have membrane-bound organelles. So they utilize this carbon dioxide in the atmosphere for photosynthetic activity. So carbon dioxide is one of the reactants required for photosynthesis to occur. It's carbon dioxide combining with water to produce a carbohydrate, sometimes the form glucose, and oxygen gas. So oxygen is a byproduct of this photosynthetic activity, but carbon dioxide is a reactant. So that means photosynthetic activity actually will absorb carbon dioxide from the atmosphere. So because it was absorbing this carbon dioxide, we saw a decrease in carbon dioxide, which led to a decrease in temperatures, and eventually we had a snowball Earth. Now, the Ordovician and Silurian event, something interesting happens here. So we had a glacial period during that transition there. And we see kind of a general rising in carbon dioxide. So the temperatures got warm enough for photosynthetic activity to occur. This is also the time that terrestrial plants started to form globally. Now, terrestrial plants, they take up a lot of carbon dioxide. So we see a large decrease in our concentrations of atmospheric carbon dioxide because of all of those terrestrial plants taking in the carbon dioxide through their photosynthetic activity. Now, more recently, 800,000 years ago, but still more recently than the OS events, we can take proxy measurements of carbon dioxide levels. So we do that by using ice cores. So the oldest ice cores from the Antarctic region provides us with an 800,000 year history of carbon dioxide levels, because as ice and snow falls and it gets compressed, these tiny bubbles of air get trapped in there. And then we can thaw out these ice cores and we can evaluate and analyze what types of gases were present. So as we can see, yes, there were some peaks and valleys, but the highest historical level is still significantly lower than the levels that we're seeing today. So the Industrial Revolution and carbon dioxide, huge increase in carbon dioxide being released into the atmosphere. So carbon was stored in fossil fuels from decomposed and decaying organic matter. And now it's being released as we burn coal, natural gas, and crude oil. So when we combust hydrocarbons, the basic formula is some hydrocarbon, CXHY, combines with oxygen to produce carbon dioxide, water vapor, and then energy. So we're combusting these fossil fuels not for the carbon dioxide but the energy. But this huge byproduct during the Industrial Revolution and still occurring today is increasing our concentration of carbon dioxide in the atmosphere. This reaction is kind of the opposite reaction that we see for photosynthesis. So here we can see this image from the American Chemical Society. We can see the Industrial Revolution occurring, and what do we notice? We see carbon dioxide levels greatly increasing. We also see methane levels increasing and nitrous oxide levels increasing. These are all byproducts from the combustion of fossil fuels. So, anthropogenic origins of these greenhouse gases. Another study done by Keeling out in Hawaii was the Mauna Loa observations. So here we see the Keeling curve. So within the curve, we do see an increase in carbon dioxide concentrations in the atmosphere. Today it looks like it's about 413 parts per million, which is much greater, about 100 parts per million greater than his start of observations in the mid to late 1950s. But within this curve, we see these seasonal undulations here. We see a peak valley, peak valley, peak valley with this increasing trend. So these seasonal changes are due to the photosynthetic activity of the plants in the northern hemisphere. So northern hemisphere has a larger land mass. So during the spring and summer months, we see the concentration of CO2 decrease. Why? Because of the increase in photosynthetic activity. Then in the fall and winter months, as cellular respiration overtakes the photosynthetic activity, we see an increase in carbon dioxide concentrations because cellular respiration, you and me breathing right now, part of that product is carbon dioxide as we're producing energy during cellular respiration. So when we look at a balance sheet between carbon dioxide, we're looking at the sources and the sinks. So the sources, those are going to be burning fossil fuels, cement production, land use, including deforestation, and intensive agriculture and animal husbandry. Then the sinks, this is where the carbon dioxide can be absorbed or stored. Some land-based sinks would be the photosynthetic activity of plants and organic matter found in soils, and also ocean-based sinks, phytoplankton, carbon dioxide being dissolved into the water, and the formation of carbonate minerals by some marine organisms. Now, while the oceans can dissolve some carbon dioxide, when carbon dioxide combines with water, we get something known as carbonic acid. So there is a concern of too much carbon dioxide in the water leading to acidification of the oceans. So here we see a general balance sheet. We have fossil fuels and land use changes. When these values are larger than our sinks, when the sources are larger than the sinks, we're going to have an increase in carbon dioxide concentration in the atmosphere. So some solutions to this. Well, solar and blackbody electromagnetic radiation, that's going to continue. So we need to look at our carbon dioxide sources and our sinks. So we need to reduce some source emissions by looking at alternative energies. There are some countries, Iceland, Austria, Peru, that have had very successful transitions to alternative energies, but also land use policy changes. So how we're using the land, making sure that we have photosynthetic activity occurring at large rates. We also want to look at increasing sink capacities. So how can we perform carbon sequestration? Where can we store this carbon? Ideally, it's going to be a combination of these two with an emphasis on looking at alternative energy sources besides fossil fuels. Here are the sources. Thank you. Have a great day.